All right, so now it's lecture 17, module 4, naive-based classifier for text classification when we use a MachineLearning, naive-based class representation.
So this is the last page of what we covered about everything we covered about generative model is already covered. But I want to do a summary table comparisons. So we covered the Bernoulli, we covered Gaussian, we covered the multinomial, right? So let's just see model. The models we covered. The base classifier and the full discrete case. And then we covered naive base discrete case. And then we covered Gaussian, the naive Gaussian. Then we covered LDA. Then we covered QDA. And then we covered MachineLearning. So this is really a lot of models. They're all in this generative base classifier category. All right, so let's just assume each of the xi, let's just assume the simple case. Can you hear me? Hello? It's okay, let me shout. Yeah. So assuming this is equal to 2 case, there are p different variables. Each one of them is x1 on 2p, and each one of them is there are 2 possibilities. Xi equals to 2, and then this is also xi equal to 2. And the Gaussian case is, okay, let's just do, So the first parameter you need to estimate is PCI or PCJ. Let's use J to distinguish J from 1 to L. So no matter what model you do, you need to estimate that OL parameter prior, right? This is just, it's not change, it doesn't change at all to whatever generative model you estimate. This is the prior distribution from the data. Okay, so what differs them is in this conditional join probability, P, x1, x2. Here I'm trying to show the size using an asymptotic form. So x1 onto xp, condition on each cj. And then this is the other number of parameter I need to estimate, right? So, and we actually reviewed in the discrete base classifier, generated base classifier case, there's no assumption I'm making. I need to do an enumeration of all the possible tabular counting, right? So how many number of parameters I need to estimate in the discrete full joint case? If you still remember, each one of them have 2 possibilities, and then x1 onto xp is 2 to the power p. Also, because generative model is conditioned on each class labels, right? Which means for each class label, I have 2 to the p parameter to estimate. Which means the number of parameter is 2 to the p times L. Okay, question, this you already know because it's asked. So when you have a naive assumption, they are all independent from each other, which makes the number of parameters in each, there's only 2, and I have p of variables to estimate. This makes the full number of parameters is 2p times L. So this we already covered, right? All right. And then let's see the naive Gaussian case. So I hope you still remember the Gaussian. Gaussian is really this mu1. Let's just use, it's a Gaussian distribution, mu1. And then in the naive case, we are assuming the sigma covariance matrix is diagonal matrix, right? Then how many parameters do I need to estimate in this case, naive Gaussian? For each class, I need to estimate mu, which is p parameter, right? So the size of mean vector is p. And then the size of the diagonal matrix is, because it's diagonal matrix, right? Each matrix, this matrix is p times p, and this vector is p times 1. And because it's a diagonal matrix, which makes the number of parameters we need to estimate in the naive case is, and then even further, the LDA case, we have different mean vector, but we have shared covariance matrix. So which makes the number of parameters we need to estimate is p plus, actually, no. So because I need to estimate the mean vector for each class, right? That's p times L, but I only need to estimate one covariance matrix because LDA assumes covariance matrix are shared. So that's p quadratic, of course, because it's symmetric matrix, that's just over 2. Not completely correct, right? If you think about this, because yeah, the diagonal terms it's not overcounted, but that's fine. So in the QDA case, we have every Gaussian has its own mu and also its own sigma, which makes the number of parameter is p plus p quadratic times L. All right, and now it's the last one we do today, which is the multinomial base classifier, which we write it as theta 1 onto theta k, condition on the C, the specific C. The number of parameters we need to estimate is the vocabulary size, which is, yeah, so that vocabulary size V in this case, then times the F. And if you look, the naive, in fact, this 2, I put it there, this 2 should be replaced into V2, right? Because it represents a Bernoulli case, but you can also expand it into like a dice or K cases, which more correct representation here is not 2 to the P, it's actually K to the P. Okay. All right. So this is everything I want to cover